Hello, everyone. So last time we were looking at Laplace transforms. And we explained how we can use this idea to solve differential equations. So if you remember, basically the idea was that Laplace transform is like a function, or basically a functional, because like functions, it has inputs and outputs, but the input here is not a number. Input is a function itself, like f of t, and the output is also a function, which we usually denote by capital F of s. So we can put the function, we can feed into this machine a function like f of t, and then go from universe of t's to universe of s's. In the universe of s's, the good thing is that there is no derivative involved. And to find or to solve for capital F of s, we will have an algebraic equation, no derivatives involved. So we can just simply solve algebraic equation using like high school methods. And then once we have capital F of s, we can go back to the original function by taking inverse Laplace transform, which is what we want to do today. Okay, so we go from f of t to capital F of s, we'll find capital F of s, and then we go back to f of t to find our function that we were looking for. And we saw that the formula for Laplace transform of a function is, let's say, integral 0 to infinity e to power minus st f of t dt. So this will be a function of s, as we explained above. And then we saw a table for Laplace transform of some functions, For example, we saw Laplace transform of 1, a constant function 1 is 1 over s. T is 1 over s squared. T to power n is n factorial over s to power n plus 1. And so on. We completed the table. Now, today I want to first ask a question. For which functions, which type of function or functions the Laplace transform exists? So that's the first question. Because the Laplace transform is an improper integral. It's integral 0 to infinity of some function. And when you have an improper integral, the improper integral may or may not exist. May or may not be convergent, basically. The limit, improper integral means limit as t go, or h goes to infinity of some integral. That limit may or may not exist, which means that the improper integral may or may not converge. So if the limit exists, then we say the integral is convergent. And if it doesn't exist, then we say improper integral is divergent. So when can we say that this improper integral is convergent? Now, I can state this as a theorem that suppose that f of t is a piecewise continuous function such that absolute value f of t is less than or equal to m times e to power ct for some constants m bigger than 0 and c bigger than 0, then Laplace transform of f of t exists. So let's see how we can prove this theorem. Proof. So we will use the comparison test for convergence of improper integrals. Recall from Math 114. Let f of t, let's say less than equal to g of t, less than bigger than equal to 0. So let's say if f of t and g of t are two non-negative functions, and f of t is less than g of t, let's say for t bigger than equal to, let's say, some capital A, for some capital A. Now part 1, if integral a to infinity of g of t dt is convergent. Convergent means that the limit exists. Limit as h goes to infinity exists. Then the smaller integral will be convergent. And second part says if the integral of the smaller function is divergent, then the integral of the bigger function will be divergent. Okay, I can also show you in the picture. See if so basically, so this is A. Or this it just could be, because see this small a and capital A, they don't have to match. But just for simplicity, just to show you in the picture, let me assume that there's just one number and small a and capital A are the same. So integral a to infinity means area under the curve from a to infinity. Now, if this is convergent, means if this area, so look at, see we have two areas here, area under f and area under g. Now, if area under g is convergent, if the integral a to infinity g is convergent, means area under g is already finite. If area under g is already finite, area under the f will be less than equal that number. So if you have a number which is already finite and you have another number which is less than smaller, so the second number, of course, will be finite as well. And the second part of the theorem says if the integral f is divergent, meaning that if the smaller number is already infinity, well, then the bigger number will be infinity as well, for sure. Okay. So here, now we want to apply this theorem. And so look at here that we have absolute value f. We are assuming that is less than m e to power ct. So this is like my bigger function. So let's see whether the bigger integral of the bigger function exists or is convergent. Now, in our case, let me set g of t as m e to power ct, then integral a to infinity of e to power minus st m e to power ct. How much is this? So this is m integral a to infinity e to power minus s plus c times t dt. So this integral will be convergent. Check that this integral is convergent if minus s plus c is negative, i.e. if s is bigger than c. Okay, it seems that the screen is freezed. Okay, so this is what I was saying, that in our case, g of t is m e to power ct, and therefore integral a to infinity of e to power minus st gt is, I can take m out, and then I'll have this integral. Now this integral is convergent if minus s plus c is less than 0. We had similar examples last time. Just write down the definition of this improper integral. You will see that it is convergent. The limit as h goes to infinity exists if, as long as this number here is negative, which means minus s plus c negative, and that's equivalent with saying s less than c. Now, therefore, for these values of s, for s bigger than c, what can I say? Hence, for s less than s bigger than c, we can say that integral a to infinity e to power minus st absolute value f of t dt is convergent by comparison test stated above, right? I'm assuming that absolute value f is less than m e to power ct. So if integral e to power minus st times this function exists and is convergent, then integral e to power minus st times absolute value f must be convergent. Because the comparison test says this, that if the improper integral of the bigger function is already a finite number, meaning that it's convergent, then the integral of the smaller number, a smaller function, must be also finite and convergent. So if now this integral is convergent, now we can use another theorem or property that says if the integral of absolute value of a function is already convergent, then the integral of the function itself must be convergent. Integral is 0 to infinity e to power minus st f of t dt is convergent. And this means that Laplace transform of f of t exists. So this last one, it was by one of the properties I said, as I said, by a property that says if, let's say, integral a to infinity of absolute value of a function is convergent, then integral of the function is convergent. Which is the situation we have here. We showed that the integral of absolute value of the function is convergent. So integral of the function must be convergent too. Okay, so one definition, if a function f of t satisfies the property that absolute value f of t is less than or equal to m times e to power ct for some constants m and c, then f of t is called a function of exponential order. A function of exponential order means the function in magnitude can be at most as big as an exponential function. And in other words, f of t has to be less than or equal to m e to power ct for some constants m and c bigger than 0. Okay, so basically a theorem that we just saw says that if a function is of exponential order, then the Laplace transform of it exists. So if a function is of exponential order, let's say if a function f of t is of exponential order, then we can say Laplace transform of f of t exists. That's what the theorem above said, and we proved it. Now, which functions are exponential order? So, of course, exponential functions and also polynomials. So here we can state a fact. Every exponential function and every polynomial is of exponential order. The reason for polynomials, let's say p of x, if you consider a polynomial, p of x, let's say a n x to power n plus a n minus 1 x to power n minus 1 plus dot 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 plus a 1x plus a 0. Why can I say that p of x is of exponential order? Now my claim is p of x is less than or equal to, in absolute value, p of x is less than or equal to e to power x for large enough x. Right? See, exponential order means absolute value of the function must be n less than or equal to m e to power cx. Now I'm taking my m to be 1, c also to be 1, and I'm claiming that my absolute value of my function, my polynomial, is less than e to the x for large enough x. Okay. So here I should have also said for constant m and c bigger than 0 and for t bigger than some constants. For some constant m and c bigger than 0 and for t bigger than a, let's say, for some a. If for large enough t, absolute value f of t is less than m e to power ct for some constant m and c, then we call the function exponential order. Now here I'm saying that any polynomial, this is a general form of a polynomial. is of exponential order, and to prove that, I have to show that absolute value of p of x is less than e to power x. Is enough to show that absolute value of p of x is less than e to power x for large enough x. Large enough x means x bigger than, let's say, some capital A for some constant A, capital A. Okay. Okay, so to prove the claim now, it is enough to show that limit p of x over e to the x as x goes to infinity is 0. Because if this limit is 0, if limit of a fraction is 0, then we can say for large enough x, absolute value of this fraction will be less than 1, for example, right? Because if the limit is 0, that means that the fraction is getting closer and closer to 0 as x gets larger and larger. So after some point, of course, it has to be less than 1 in order to be able to get closer and closer to 0. Even I can say after some point is less than 0.01, right? But right now, even if I say that this number in absolute value is less than 1, this number here in absolute value less than 1, that will be equivalent with saying that absolute value of p of x is less than e to the x, right? If absolute value of the fraction is less than 1, means absolute value top is less than or equal to absolute value bottom, which is equivalent with this. So to prove the claim, it's enough to show this. And to show this limit is 0, lastly, to prove that this limit is 0, what do you think we should do? Apply L'Hopital's rule. So limit p of x over e to the x goes to infinity, equals limit a(n) x to power n plus a1 x plus a0 over e to the x goes to infinity. Now this limit is of the form infinity over infinity, so we can use L'Hopital, which means we can differentiate top and differentiate bottom. So limit n a(n) x to power n minus 1 plus dot 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 plus a1 divided by, but derivative of e to the x is still a to the x. And if you continue, apply L'Hopital's rule, n times then we get at the last time, you will get n times n minus 1 n times n minus 1 times n minus 2 all the way to 2 times 1 times an divided by e to the x. But so numerator after n times differentiating becomes this number, but denominator still e to the x, because e to the x derivative is e to the x, and therefore e to the x remains e to the x even after n times differentiating. Limit of this as x goes to infinity. And now this is a constant over infinity because the numerator is constant. Denominator is e to power infinity, which is infinity. The answer is 0. So we show that polynomials are of exponential order, meaning that absolute value of polynomial is less than e to the x for large enough x. Now, this is for proof of polynomials being functions of exponential order. Now we can also prove that exponential functions are of exponential order. Let me leave that part as exercise. Show that every exponential function of the form, let's say f of x equals a to power x for a bigger than 0, a not equal to 1, is of exponential order. All right, so this is about the question of existence of Laplace transforms. Now we want to look at the uniqueness. The question here is this: assuming that the Laplace transform of let's say some function f of t exists, say Laplace transform f of t equals, let's say, capital F of s. Then can we say that f of t is the only function with Laplace transform f of s? In other words, we are asking whether Laplace transform is a one-to-one transform or no. Because in the next step, we want to take or apply Laplace in inverse Laplace transform. Therefore, it's important whether the Laplace transform is invertible or no, meaning whether it's one-to-one or no. So how can I check that whether a function, or in this case, a transform, is one-to-one or no? We have to see whether we can have two different inputs with the same output. Is that possible to have two different inputs with the same output? If that is possible, then the transform is not one-to-one. Otherwise, it is one-to-one. So in other words, is Laplace transform one-to-one? So the answer lies in this theorem that shows it is one-to-one. So suppose that f of t and g of t are functions, are basically continuous functions which are of exponential order, and also suppose that Laplace transform f of t is equal to Laplace transform g of t, meaning that capital F of s capital f of s equals capital G of s for s bigger than c, for some constant c. Then we can say that f of t equals g of t for all t bigger than or equal to 0. Okay, so if Laplace transform of two functions are equal ultimately, meaning that for s bigger than c for some constant c, then those two functions must be equal to themselves for t bigger than or equal to 0. And remember that in the context of Laplace transform, we only care about the restriction of the domain to 0 to infinity, because remember, Laplace transform is an integral on 0 to infinity of e to power minus st times f of t. So here, basically, in the context of Laplace transforms, we consider the domain to be 0 to infinity. So when the theorem says f of t equals g of t for all t bigger than or equal to 0, basically it means that f of t and g of t are equal on their domain. Okay, so based on this theorem, we don't want to prove the theorem, so we'll just accept the theorem. So for proof, we'll skip it. But now, based on this theorem, we can conclude that Laplace transform is 1-to-1, right? Because if the outputs for two different inputs are equal, then the inputs must be equal. And that's exactly the definition of 1-to-1 function, in this case transform. That if two outputs are equal, then the corresponding inputs must be equal. So based on this, we can conclude that Laplace transform is 1-to-1 and hence invertible. Now, given a function f of s, and inverse Laplace transform of f of s, denoted by inverse Laplace transform, is defined as the unique function f of t such that Laplace transform of f of t equals capital F of s. So this is exactly the concept of inverse function that you learned in pre-calculus. So for example, when I say f inverse of 3, let's say equals 7, what does that mean? This means f of 7 equals 3, right? Inverse function changes input with output. In this case, inverse transform changes input with output. So when can I say that L inverse of capital F of s is a small f of t? If L of small f of t is equal to capital F of s. And according to the theorem, we know that given, let's say if I have a fixed function capital F of s, there is only one function small f of t, such that Laplace transform of small f of t is capital F of s. Because the theorem says if Laplace transform of another function g of t is also capital F of s, then small f of t and small g of t must be equal, meaning that there's only one function, small f of t, with this property. Because if there's another function, that function must be equal to small f of t. So there's actually just one function. Okay, so there's only one function that Laplace transform that function is capital F of s. That function is defined as L inverse of capital F of s. Okay, so for example, inverse Laplace transform of 1 over s. What is this? Well, we are looking for a function, let's say small f of t, such that Laplace transform of small f of t is 1 over s, right? If you want inverse Laplace transform of 1 over s, that means you're looking for a function f of t, small f of t, that Laplace transform of small f of t is 1 over s. Right, so this is like the Laplace transform that I said you can view it as a box. So I know that 1 over s is here. I want to know what is the original input. When you say L inverse of 1 over s, that means 1 over s is an input for Laplace inverse Laplace transform, which means it must be an output for original Laplace transform. So for original Laplace transform, 1 over s must be output, and then there will be some input corresponding to that. Whatever that input is, that will be my answer here. Now, in order to find out about this, I can look at my table to find question mark above. See the table we derived last time. So look at the table. Table says, if f of t, small f of t is 1, then capital F of s is 1 over s. So, and that's exactly what I was looking for. I was looking for Laplace transform of which function is 1 over s. But this table says Laplace transform of 1 is 1 over s. So according to the table, you can say Laplace transform of 1 is 1 over s. So question mark equals f of t equals 1. Or similarly, you can do it for inverse Laplace transform of 1 over s squared. Again, you can say according to the table, Laplace transform of t equals 1 over s squared. So that means inverse Laplace transform of 1 over s squared is equal to t. So here basically f of t equals t. Okay, guys.